Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. I'm Alan, and I'm still with you in the chemistry lessons. I hope you're safe and still following the Ministry of Health regulations about how to overcome COVID. So today we are still on Unit 15, which is about radioactivity, and we are heading in for Lesson 3, which is on radioactive decay equation and its applications. So as you can say, radioactive decay equation, you see the word equation. So I expect you to be having your calculators, scientific calculators actually, not simply any calculator, but scientific calculator, because we are going to be making calculations involving lean and log and so on. So, as we're getting started, remember I had given you the exercise in lesson 1, which we called it exercise 1. I gave you all this time for you to quickly understand the whole aspect and attempt that exercise. You're seeing it on the slide, but right now I want us to focus on the chalkboard, so as we can go through that exercise together. Let's focus on the chalkboard and we'll do that exercise together. I've picked the crucial parts. You see, like question 3, I left it out. Question 5, 6, 7, I also left them out. I picked the crucial part, which can give us the whole idea for the interest of time. In that way, when we've gone through all this, you should be able to go and finish up the rest, or compare your scores, or compare your answers with what would be expected. So, the question was saying, complete this nuclear equation. Remember, they are nuclear. The reaction is taking place within the nucleus of the atom, not the electrons outside the nucleus. So that's why they are called nuclear equations. Then indicate the type of decay per each nuclear equation. So, how do we get the value here? Let's quickly go through it. You see, it has to balance. The value on this side must balance with this side. We have 2, 1, 4, 8. This is mass number and the proton number. So, indicating the difference here is 84 minus 82, which will give you a 2. This minus this, which will give you a 4. So when that happens, you now need to look into your periodic table. You need to be having the periodic table with you in this part. Look at the periodic table on the slide and see, where are we? This is the atomic number, which is a 2. Remember, elements in the periodic table are arranged according to the atomic number, or the number of protons. Now, let's focus back on the board. You see this 2, it will determine which element it is. And as such, this is a helium. From the understanding we've looked at, this is alpha decay. This is an alpha decay. If at all you don't write the word decay, it's okay. It still remains decay. So that is the first. It is an alpha decay. Now looking at the second, you have here, and get this value, subtract this value directly. 2 minus 4. No, we want this, so we shall get 2. This is a 218. And this value here, subtract this, you will get simply 84. So now, 84, we go back and check on the periodic table where we have 84. It is just after bismuth, and that is polonium, so it is PO. Also, this is alpha decay. This is alpha decay. So this is for helium, or helium decay, or alpha decay. That is how you quickly get the answer. What about this? Remember, we're having a -1 here. So indicating this will be 83. This plus this should get you this value. This value plus the value here, and this, no. To get 214, we shall get this value here plus 0, indicating this remains as 214. The element, you look into the periodic table, this will be directly bismuth, 83. So, what is the decay here? As we looked, this is a beta decay. Like that, and you come also in here. This is 92, this is 93. Get 93, subtract 92, you will get 1, but because this has to be equal to here, this is a -1 here. It has remained the same, so indicating we have a 0, and this is our electron, or you can put beta, it's up to you. So this is the value. So basically, that is how you quickly balance. It is the usual subtraction and addition of the ordinary chemistry, or the ordinary math for those. Lastly, number 9. Number 9 is quite different from what we've looked at. This is artificial radioactivity. You're bombarding lead with a helium atom. So we don't expect any type of decay here. So we are bombarding these two, and the answer here will be 210, and this becomes 84. So what is the value of 84? We're already having it here as PO. And that's it. So that is how you quickly do balance those equations with the help of the periodic table, then you fill it up. Okay, so for today, we are going to be looking at radioactive decay equation and its application, and basically our objectives are we should derive it correctly, then apply it accurately. Without taking much more time, what is that integrated decay equation? Any integrated decay equation, Nt equaling to n naught exponent negative lambda t. This is our decay equation. We are to derive it and explain what exactly it implies. So, before we even go into deeper derivation, as you see, we are having exponent. So this equation tells us that the radioactive decay it has an exponential increase with time. We are having the lambda, which is the decay constant, and time. Exponential. So the radioactivity will always occur provided you have unstable atoms or you have an unstable nucleus. It will always decompose and decay until it attains stability. That's what is meaning with spontaneous decrease. And the illustration is just on our slide. If we can focus on our slide. Strontium, if it starts with 100 grams, it will always decay until it can even reach 0. But the stopping point is when it attains stability. So this exponential decrease is what this E implies, that exponential letter. So today's focus is to derive where is this expression coming from. Now let's go through it and derive it. After understanding what it implies, basically, let's now derive it. So the starting point is to notice that radioactive decay is random. It's random first order reaction. Remember the order of reactions? Yes, it's a random first order reaction. So, using our N, actually something I need to emphasize here, this N is not a mass that you always have to be using N. In some books, you will find they are using A. They are using A, lambda T. In other books, you may find they are using S or any letter, as we are coming to see what they imply. So suppose we are having N atoms of an element decaying or disintegrating to give some products. Again, when you're looking at orders of reaction, the product doesn't really take much of our focus. So if we're having this, then we determine the rate. The rate, remember, for the first order is directly proportional to the concentration, to the amount you're having. So in this case, rate will be directly proportional to the number of atoms I'm having. For me to remove this, the proportionality sign, I will say rate is equal to lambda n. What is lambda? Let me use different color here. So, where now our lambda is the decay constant. And it's normally per second, or it is considered in terms of the in seconds that have elapsed as decaying is occurring. And we take our N as the number of atoms disintegrating. The number of atoms disintegrating. So, with us defining these two, let's recall back. Remember how we get the rate for a reactant, which would be a change, minor change, delta N, the number of atoms, with as time changes. But because these are decreasing, they are disintegrating, we include a minus. The minus implies the decrease. The decrease in the number of atoms with time. So we have this and our, let me call this 1 and 2. Can we equate these two? 1 and 2 equations, you will find we are having negative change in N with change in time equaling to lambda N. The next step is to separate the variables in here. And we end up having, let me just write it directly here, change in number of atoms over the N is equal to, I will take this minus the other way, negative lambda delta T. I brought this here, I took this their side. Now, when we reach here, the next step is to integrate. And of course, integration comes with limits. So let's integrate within limits. Now the part is to get in the limits. What are those limits? If we take n naught as the number of atoms at the start of this integration, the atoms you're having before the decay happens, and that is at time which is 0 seconds. We also take our nt to be number of atoms at a certain time. Let's call time to be t. Now you see where the nt and n naught comes from? The limits. So if we had to integrate, putting in limits, you'll find you're having from n naught, the lower limit, to nt, the upper limit, divide, this directly implies it is 1 over n, change in n, equaling to negative lambda. This is a constant, so we don't put it in the integral sign. From time equaling to 0, when the disintegration has started, to time which we can call t, any time during the disintegration with change in time, delta t, change in time. So we have this integration equation. The next step is to bring in the rules of integration. Again, to the PCM and to those taking math, this is kind of a repetition. To the PCB students, you also go through this in your sub-math lessons. So let's apply the rules. The first rule we are going to use is if you're having integrating any value, this is equaling to ln of that value n. We are integrating 1 over n, which is same as ln this. And ln number, if you have ln number equaling to x, that implies n is equal to exponent power x, or the exponent x, 10 power x, which we call that. So we have these two as our rules of integration. Now, we have to bring these rules into our integral equation. So what does this imply? Ln, remember I told you to come with calculators, now shall be substituting ln. Ln n within the limits n naught to nt is equal to minus lambda time t minus 0. The highest minus this. So directly this gives us ln n, the highest, minus ln lower limit is equal to negative lambda t. T minus 0, that is t. Now, let's go on and shorten up this. Using the rules of logarithm, since we are subtracting, it is same as saying ln into nt minus n naught is equal to negative lambda t. At this moment, we bring in our rule 2. This directly means nt over n naught is equal to exponent negative lambda t. Exponent, then the value. 10 power that component. If we rearrange, you'll finally get our final equation, which is nt equaling to n naught. I'm taking this to this side. Exponent negative lambda t. And this is our decay equation. We are going to be using this decay equation now and again. Why am I bringing it in here? In the process, you can take it back and have this. So this and this. We are going to be substituting them now and again. This, or this, whichever, ln n naught over n equaling to negative lambda t. So at least make sure you understand these two equations. We shall be applying them. I again come to highlight the aspect. This decay equation tells us that the disintegration of radioactive atoms is exponentially non-stop, or the decrease is exponential. It does not stop until stability is attained, or until you have 0 atoms, if that is when stability can be attained. So that is how you can derive it, and you get your decay equation. Next part of our objective is to apply it. Yeah, we are to apply it. So we can apply it by using that practice question. Practice question. Let me clean up the board so as we can have where to do the calculation from. So, what is the question asking us? They're saying a certain radioactive phosphorus decay is found to be 30% complete at the end of 50 minutes. Now you may wonder, how do they come to that? That is carbon dating. Remember, I left you with the exercise to read about how carbon dating is exactly done. Now it is time to apply that knowledge in this part. So you're having 30% at the end of 50 minutes. We are to calculate decay constant. We are to know what is that constant that the amount of phosphorus continuously decays. So let's go through that. And to go through it, we need to extract what we have. We have at time equaling to 50 minutes. We need to change minutes always into seconds, and that involves 50. Convert this to seconds times 60, which will become, quick math, 3,000 seconds. So they're saying it was found to be 30% complete at the end of this, indicating our N naught will be 100%, since it is in terms of percentages. And NT will be 100% minus 30%, which is giving us 70. Why do I subtract? Why do I have 70% as NT? The number of atoms present after 50 minutes. I need you to critically interpret that question. A radioactive decay for phosphorus was found to be 30% complete. 30% complete, indicating if you're having this as 100, or maybe call it 1, you're having 1 atom of phosphorus, and it is breaking down. After 50 minutes, 30% has disintegrated. You see, this part has gone out. So what do we remain with? We shall remain with what you had minus 30. This nt implies the amount present. It is not implying what has disappeared. Remember? So, in this way, it becomes 100 minus 30, which is 70. So, with our n naught and nt and time, can't we substitute? We can use, let's use ln n, our formula nt over n naught equaling to negative lambda t. Substitute directly. Ln 70 over 100 is equal to negative lambda, the value of t, which is 3,000. So, lambda, this is taking this over here, will be going to our calculators. How do I get ln? Look clearly here. On your scientific calculator, there is ln here. It is the third button from on. From on, it is the third button. And as such, you just go to your calculator, press in ln of this value, 70 over 100, divided by 3,000, but this is now going to be a negative here by 1,000. Then you get the value. The value will be positive because the negative here will cancel with the negative from ln. If we can quickly substitute, it is 1.189 exponent negative 4. And this is per second, because this is in a second and ln has no unit, and it becomes per second. So just use the same equation to obtain the time needed. For part B, if I can quickly interpret it for you, it will simply be, since the nt will be 100 minus 90%, which gives you 10%. So use nt as 10. Substitute, you have your lambda, substitute it in this equation to get time. For the interest of time, the answer here should be, you calculate, you'll get some answer 3.222 minutes. Please, I will not go through that. I'm giving you the answer. Follow the same approach and get the answer. So that is it, and as usual, I can't leave without giving you the exercise, and that is the exercise. I call it exercise 3. Try them. At this moment, you know where these formulas are coming from. It's a matter of substituting. Thank you for participating in this lesson. I'm happy to still be teaching you. Please stay safe. I want to see you in the next lesson. Alan is my name. Bye.